Now I'm pleased to introduce our presenter for today's training, Brian Gettinger, PE. Brian is the tunneling service leader for Freeze and Nichols, providing the technical and project leadership on tunnel projects across the organization. He has a wide variety of experience in design, cost estimating, inspection and construction management of tunnels, and grouting of shafts and reservoirs. His tunneling experience includes hard and soft rock tunnels, excavated by conventional tunnel boring machines, EPBM, and drill and blast methods with tunnel liners, including cast-in-place concrete, precast gasketed concrete segments, and fiberglass pressure pipe. He is a registered civil engineer in the states of Texas, California, and Missouri, a graduate of the University of Missouri in Kansas City with a bachelor's in civil and a master's in business administration. Now, invite Brian to make his presentation on risk management for underground construction.
All right, Bob, thank you. Hope everyone can hear me okay. Excited to be here today. I guess I did a presentation, maybe it was in April, right at the beginning of the coronavirus. Apparently I did a good enough job that I got invited back, so I appreciate the opportunity today to talk a little bit, maybe a little more detail about tunnels, particularly around risk management. Last time was more of a focus on tunnels in general. So today's focus is on risk management, which is really important to a successful tunnel project. So our agenda today, what are we going to talk about? Do a quick introduction of myself, talk about underground construction in Texas, what's happened and what's going to happen in the future. What are the principles of risk management we're going to apply to underground construction projects? Why tunnel? Geotechnical investigation and testing. GIR, GDR, GBR, what's the difference? Some examples from baseline reports and some best practices, and then have a chance to ask a few questions at the end. So let's jump into the topic today. So if you saw the presentation in April, you saw the slide. I need to get a new family photo taken. My wife told me that actually yesterday. But I have 3 little kids. We live in Houston. Been here for 3 years since Hurricane Harvey. Went to the University of Missouri, Kansas City. My undergrad's in civil engineering. My master's is in business. So I am not a geotechnical engineer nor geologist. So I am in a lot of cases, in this case, interpreting information provided by others and helping, in a lot of cases, owners and clients understand what those risks mean, and maybe in simplified jargon. But I don't try to say I don't masquerade as a geotechnical engineer, but we're going to talk about geotechnical risk a lot today. I lived in California long enough to get my PE, and I left, and then saw the light, came to Texas. So here I am. If I do ever see people in person, it's hard to tell this on a video conference call, but I am 6'8". So at a conference, I am quite easy to identify. I'm also very effective as a rallying point. If you need to find a group, to say, find Brian, and everyone at that point, I got a crowd. Hope to get to see folks in person sooner than later. Hopefully much sooner, with the possible vaccine coming. So, all right, talking about tunnels. So underground construction in Texas, where are we at? What's the state of the industry? So there's quite a few projects that have been constructed, major tunnel projects in underground caverns and things in the state. Folks remember back 20 or 30 years ago, there was the super collider that was studied extensively. That was in the up in North Texas near Waxahachie. It wasn't constructed, but there was a lot of great geotechnical information collected on that project in the shales and limestone layers around the Dallas-Fort Worth area. Still quite applicable today because the ground doesn't change over 30 years, right? Talking about millions of years, it changes. So all the major metropolitan areas in the state have had tunnels. The ones in black here are ones that have been constructed, and the ones in white are either under construction or planned to be constructed in the future. So Houston was kind of behind the curve on this, maybe compared to some other cities, but we're working on catching up with some of the wastewater, water, and maybe stormwater projects here in the future. So speaking of Houston, Houston has actually a pretty extensive network of wastewater tunnels that were constructed by either two-pass, open-face machines, or by microtunnels over the last 20 or 30 years. There was a time that Houston was on the front page of the Trenchless Technology magazine for tunneling capital of the world, right? That a lot of that slowed down, but it's going to pick back up again. The interesting point as it relates to this presentation is that these tunnels were all constructed without geotechnical baseline reports. And in many cases, environments that a lot of risk was placed on the contractor, and a lot of the decision making was placed on the contractor. So I think it's important to state that we have industry best practices now we'll talk about today. It doesn't mean that they have to be used, but they have been shown to be effective at managing contract bid prices, reducing change orders during construction, and making everyone's life less hectic and painful during construction, because nobody likes change orders. But tunnels have been constructed for a long time, in a lot of cases without some of the things we'll talk about today. But I think we can do better going forward. That's what we're going to talk about in this presentation. All right, so principles of risk management for underground construction. Kind of start at the beginning. So it's important to recognize that underground construction is a lot different than surface construction. So for civil engineers, surface construction may mean a road project, right? Highway project at grade roads. It may mean structural support for buildings and things. So on a surface project, you've got well-known surface conditions. The construction is generally complicated, right? You know, building a high-rise building is a very complicated project. Even a lot of the big interchange projects you see TechSod doing are very complicated, but the constraints are pretty simple. Oftentimes, the critical path project has a few different ways to solve the challenge. On an underground construction project, the critical path is very long and very linear, and has very few workarounds. We only know some of the conditions, right? A surface project interacts with the ground on one side, right? In our case, in the tunnel, we interact with the ground on all sides. We're surrounded by it, and we only have limited data. Even the most robust investigation advancement project, borings every 300 feet or every 200 feet, it's still a limited sample. The construction is generally very repetitive, right? It's doing the same thing over and over again in cycles, and very few workarounds. So because the risks are different, there's some different contracting tools and approaches to mitigate that risk. I really like this quote: surprises are inevitable. There will always be unexpected ground conditions, and either the owner or the design team can completely eliminate surprises from complex underground projects. So uncertainty always is going to exist. We can never eliminate it, right? But our confidence can increase, and the likelihood of consequences can decrease, and the size of those consequences can decrease through risk management. Risk management strategy reduces cost uncertainty, and that's always one of the big questions. So what is this project going to cost? And early on, it's, well, what does it cost to build? But then, an owner, they need to know what is it going to cost to construct, and the bid price is not always the final price. When I was living in Ohio, there was a job that bid in Akron, a big tunnel project, and the engineer's estimate was $240 million, and the bid price came in, engineer's estimate, $240 million. The bid price came in at $185 million. And the front page of the paper the next day was City of Akron saves $60 million on tunnel project, but they hadn't actually built it yet. So we don't want to count our chickens before they hatch, right? The bid price, getting a good bid price is really important, right? And risk management strategy affects that. But a job costs what it costs when it's finished, not when it bids. So risk management helps us get a better bid price up front. Also is going to help us manage the changes and uncertainties during construction to ensure that when we get to the end, we've met our budget as best we could. All right, some more facts on tunneling. So in the middle is kind of the central point that I want to hit home today is contractors don't accept risk, they price risk. So Houston in the past put a lot of projects, a lot of that risk on the contractor. They didn't have a baseline report. They told the contractor to figure out the means and methods, right? And the contractors accepted that risk, but they don't accept it for free. When they take risk, they're going to put a price on that risk. Some contractors have a higher risk tolerance than others. That's why you often see varying bid prices. But we can't just assume that they're going to take risk without paying for it. You know, owners want the lowest cost. Contractors that anticipate risks will have lower costs through claims, right? Giving them good information helps them anticipate those risks. The conditions they're going to encounter significantly influence the design and construction costs. Tunnels are often long, right? Miles in length, or even thousands of feet. It's still long. That's still a long piece of infrastructure. And the conditions vary along that alignment. It may not be the same for the whole length, or the whole same depth, right? Digging a deep shaft might not have to be the same all the way down. It's better to anticipate a risk than be surprised when it happens. And underground surprises equals commercial risk, which equals dollars. So those are all facts of tunneling, and that affects our approach to risk management. All right, so some things that can be allocated to the contractor and should be allocated to the contractor. The range of anticipated conditions that you encounter on the ground. So the GBR stands for Geotechnical Baseline Report. Those are going to be outlined in the baseline report, right? The means and methods the contractor can use are his risk, right? Consistent with what the GBR and the contract specifications allow. The quality of the work, right? And the ability to meet cost and schedule. Those are all things the contractor can be allocated. But you want to allocate that risk fairly, and using a GBR is considered a best practice and fair because you want to attract the highest caliber contractors. In most cases, still, we're using low bid construction contracts, which is not inherently a problem, but we want to make sure those people that are attracted understand that the market is fair for the bidding. When we have a fair bidding with good information, we generally have more closely spaced bids because everyone's relying on the same data set to develop their documents. No one's going out on a limb, drawing conclusions off limited information. If we do have disputes, we have a baseline report. That baseline sets a baseline that allows us to say, okay, this is inbounds or out of bounds. That allows us to avoid litigation and save heartache and time. And when we're building a project, the one person who we don't want to pay is lawyers. And lawyers love to be paid, and we want to avoid paying them. And some of these risk management tools will help us avoid doing that. So, who ultimately owns the ground? Who owns the ground? This has been litigated in a lot of projects. There's different strategies on allocating risk, but at the end of the day, if something strange is uncovered, the owner always owns the ground. So it's in the owner's best interest to fully vet what the ground conditions will be with the investigation and to tell the contractor what to expect with the data report and how the ground's going to behave, what you should assume with the baseline report. So risk management is a process. It is not something you do at 30% design, something you do at 60% design, 90% design. You don't do it at the pre-bid meeting during construction. You don't do it when you have a problem. It's a process that you're going to do at 30, 60, 90 pre-bid meeting during construction. You're going to print the risk register up and put it on the side of the trailer, and for the contract team to work on during construction. It's a process that's going to be revisited throughout the project. It needs to be part, kind of the central tenet of the project. One of the main focuses of the whole team is how do we manage risk? It should be a discussion that's happening often, not only amongst the engineering and geotechnical team, but amongst the engineering owner, and obviously once the contractors are involved with the contractor as well. A baseline report, we'll talk about that a lot today, is a tool. It's not the only tool, and it's not a magic bullet, right? You need to use the tool also effectively. Hammers like to find nails, right? Hammers don't do very well and hit a screw. So we need to have the right tools for the right situations. Some of those are talk about risk registers. Another one is expertise, having professionals and contractors that know what they're doing, have been through this before, that can apply lessons learned is really important. A lesson learned is great because it's a lesson learned by somebody else that we don't have to learn again, right? The definition of insanity is repeating the same thing, expecting different results. So let's use our expertise and prevent those things from happening in the future. And then communication. If we're not communicating, things are going to go awry one way or the other. So we got a little flow chart there. Number one, identify, right? Got to identify the risks. You need to assess the risks. How likely is it and what's the consequence? Take action, avoid, mitigate, or allocate it, and then repeat. So that, I like that graphic, but it doesn't necessarily do a great job of explaining that this is a repeating process. So here's another way to look at it. It's the risk management loop. Identify, evaluate, mitigate, allocate, avoid, repeat. Proper execution of risk management is going to result in lower bids that are more tightly clustered, allow people to carry, owners to carry reduced contingency in a construction contract so that they have confidence they don't need to go back to the board or council for more money. And it's going to end up in a situation where the odds are that your contractor, the engineer, and the owner are going to be much better friends at the end of a construction project than they otherwise would be if they had a bunch of challenges. And in orange there, the experience of professionals is key for reliable management of risk. I can't repeat that enough. This is not something that you want someone doing their first time. And so when we're qualifying both engineers and contractors for projects, we want folks qualified that know what they're doing, that can say, okay, I've done a project in this kind of ground conditions with this kind of method, whether it's a microtunnel or an HDD or a tunnel bore machine or a certain type of tunnel bore machine. And I've used it in this kind of ground with this kind of pipe for this similar length. That's what we want. Someone has done it before. We don't want somebody to say, oh, I've done a 1,000-foot long microtunnel, I can do this 5-mile long tunnel. Those are two different things, right? So we need to make sure if we're using pre-qualification, which we should if we can, we're qualifying for the right things. All right, so how do we take action for risk? Okay, so avoid, number one. If we can just avoid the thing, that's the cheapest and best solution. Change the vertical alignment, change the horizontal alignment, specify certain methods of construction, like a pressurized face tunnel machine versus a non-pressurized face. Avoid the risk, but not always possible. Okay, so say we can't avoid it, then we go to mitigate, right? If we know there's a risk, right, how can we mitigate it? Do we do a couple more borings? Do we do some testing for swelling pressures, or do we do some testing for a test that's going to test the hydraulic conductivity of the ground conditions with a slug test and a piezometer? How can we mitigate it, right? Can we mitigate the likelihood of occurrence, right? Or can we mitigate the consequence if it occurs, right? Could we do some pre-excavation grouting in an area that's unstable? So it doesn't necessarily eliminate the instability, but it reduces the consequence of the instability happening. And then allocate the risk. Allocation is incredibly important. We need something to be accountable. So partly that's setting baselines. Okay, here's what is inbounds and out of bounds. Here's what the owner will take on as risk, and here what the contractor should take on as risk. And you allocate that risk to the party who's best able to control it. So I've mentioned this a couple times, but I want to reinforce the point that we're talking about two different scales here. One is the likelihood of a risk occurring, which is shown here on the bottom, 1 through 5, on the right side of the screen. And then on the left side of the screen, we've got descriptors. And we also have consequence, which is also on the 1 to 5 scale. So the likelihood, is the likelihood 1? Is it improbable? 1 in 1,000? I mean, theoretically could happen, but not likely. Or is it frequent? It's expected to happen. Is it something that if a consequence happens, is it a really bad thing? Or is it not a big deal? So you have 3 different areas here, white, yellow, and red. Red risks are our priority to focus on first, right? So those include very low likelihood events, right? Likelihood of 1, but a consequence of 5. Those are often your life safety and a tunnel major settlement. So if we're crossing on a railroad track, right, the likelihood of it having settlement may be very low, but consequence will be very high, right? Once the red ones are covered, and the goal is to push risks down. So if it's red, push it down to be yellow, and if it's yellow, push it down to be white. So work our way through the process, but focus on the highest consequence risks first. So how do you determine the consequence of a risk? This is an example from a project, tunnel project, but this is something that, as you note in the very bottom tagline here, consequences should be customized for each project's instance. So a product that costs $500 million is going to have a different feeling about financial risk than a project that costs $1 million. An owner that has a giant capital budget is going to have a much different thought about financial risk than one that has a small one. An owner that has to go back to city council for approval of any change orders is going to have a different feeling than one who doesn't. So every project is going to be different here. Some categories that we often look at for risk registers on projects is, okay, financial, right? Project schedule impacts, public stakeholders, regulatory and legal, health and safety, operating and maintenance, and natural environment. Those are not necessarily always applicable to all projects, but it's a pretty good starting point. And there may be others that you want to add or reinforce with additional clarity. But you can see, financial risk here, insignificant is less than $100,000. Catastrophic is more than $10 million. Project schedule impacts, insignificant 7 days, catastrophic is 9 months. Again, going to vary on projects. That's our consequence rating. So what does that look like? So if we go to say, okay, here is a risk register. This is a list, part of a risk register. And this is focused on logistics and construction issues. So problems with the tunnel, the risk is tunnel excavation doesn't do well with the ground conditions. So the contractor is going to achieve low productivity because of the planning, logistics, lack of qualified labor. Anyway, the tunnel's not going to go well, right? Consequence of that is scheduled delay and probably some claims. Generally, tunnel projects, if they have a scheduled delay, they're going to have a change order for claims because the time, equipment, very linear, costs a lot of money to make up. So that's risk likelihood of 3, middle of the ground, right? But schedule impact can be significant, so it's a 4 on that. Well, the combined risk score, 3 times 4, so whatever the risk likelihood is times the maximum consequence is our risk score of 12. So what do we do? What does 12 mean? 12 means really nothing. It needs to be compared to the other risks in the project. But in this case, it highlights a yellow risk. And that means, what are we going to do? Well, one of the ways we can mitigate that is minimum tunnel requirements for a contractor. Try to make sure that the person who gets the job has experience with it, right? That'll reduce that. And what we do is actually another set of columns to the right here that doesn't come on the screen very well. You re-rate the risk. So, okay, I implement these control measures. Now what's likely the risk? Is it now a 2 instead of a 3? And if that's the case, then now that risk isn't a 12, it's an 8. And that may push it down to a point where we feel better about it. This is a way for us to not only make accountability for who's responsible for things, but also to say, okay, we now have mitigated that and we tracked it in the project record. So we could spend many hours talking about risk management. I've seen there's other great presentations on this. But as a high level effort, here's some key points. Risk management's a process. GBR is only a tool. The owner owns the ground. No one's going to accept that risk. They're going to make you pay for it. Experience of professionals is key. And risk registers are a helpful tool to both visualize and drive accountability. So literally, I've seen these risk registers printed in giant form and stuck to the wall of construction trailers so that every meeting, when everyone's in the room, back when we had meetings in person, they can say, okay, what's the status on this? And they can even fill it in to make sure that everyone's being accountable. So risk management, really important. GBR is a tool. So let's talk a little bit more about both investigations, because we need data to do a GBR, and GBRs themselves. All right, so geotech investigations and testing for underground construction. What are we trying to determine? Well, we're trying to determine how the ground is going to behave. So there's a ground behavior classification called the Tunnelman's ground classification, and it's going to talk about how the ground is behaving. So soils, is that soil firm? Is it swelling? Is it flowing? Right? Is the bedrock massive, swelling, squeezing? Is it abrasive? Is it karstic? All those characteristics are important because they're going to affect how the ground behaves. Is the groundwater flowing? Is it going to be able to seep in at a very high rate, very low rate? Is there artesian pressure in the groundwater? Right? Does the groundwater fluctuate with rainfall, or is it pretty static? All those things. That's what we're trying to classify with the geotech investigation. We don't do investigations just to drill holes in the ground and do lab testing, right? I didn't particularly enjoy my soils lab in college where we had to do Atterberg limit tests. We weren't doing the test to do a test, right? The ASTM exists to give us data to inform us on ground behavior. So what kind of tests should we be doing? So I'm not going to go through each one of these, but there are a lot of tests that can be done both in the field and in laboratory to help us determine these properties. Some of these are done by drilling a hole, right? Collecting a sample in a thin wall tube or in a Shelby tube. Some of them are done by driving a CPT, cone penetration test, and essentially driving a rod into the ground. Some of them are done by testing the groundwater, putting in a monitoring well or gasometer, so we can test the groundwater both by its chemical content, test it for how quickly it moves in and out. There's a falling head test, rising head test. There are slug tests, all kinds of things you can do to test conductivity in soils. And rock, you also can do packer tests as well. And then all kinds of tests, and they continue to come up with more of them. One at the bottom here, soil abrasion test is a newer one that's done kind of by the Colorado School of Mines that tests how abrasive the soil is. Is it going to wear down excavating equipment over time? But key point, how is the ground going to behave? What tests do we need to do to determine how the ground is going to behave? So for bedrock, again, there's more tests, and certain bedrock units, certain types of material, whether it's shale or limestone. If you get outside of Texas, we might get into some other metamorphic kind of rocks. Different tests may be appropriate. RQD, the rock quality designation, is really important. How fractured are the samples? When do we hit water, right? How abrasive, again, is it? Does it swell, right? Is it going to squeeze? How does it behave when it's wet? How durable is the material? All these things are going to help us inform how we excavate into the tunnel. So I saw there's some geotechnical folks on the phone. They're going to be disappointed. That's all I talk about today on testing. There's a lot of stuff there, right? And I believe these slides will be made available to you guys after the meeting so you can review those. That was not a comprehensive list, but it was a good start. Looking at geotechnical work plan for a tunnel, what you would put in there, a good start. So things you should do, best practices. locate a boring within the envelope of every shaft. I was talking to some other geotechnical engineers with Briley Associates we work with on a project that came up. And it's a great point because we want the contractor to know exactly what he's going to excavate for that shaft. Well, the best way to do that is put a boring right in the middle of that shaft, and that'll help us find out. If you do a piezometer, though, keep it outside the excavation because that way, that piezometer you can install during the investigation, 30 to 60% design, and then you can keep it active. Or you can monitor the water in that piezometer for time, and then during construction, you can monitor during construction, make sure that the either the watering operation is working right, or that you aren't affecting the water source elevation. You have a watertight shaft, and then the contractor can fill it in later. Drill borings at least 20 feet or 2 diameters past the invert. We want to know what's beneath us. We don't want to know what's. So say you're in a good clay, right? But there's sand, a whole bunch of sand beneath you. That's going to affect the invert of your shaft and your tunnel. We want to know that. Locate a boring every 500 to 1,000 feet along the alignment. In some cases, maybe closer, maybe even 300 feet along the alignment. And one, do not drill borings through the tunnel alignment. Offset the borings a little bit. In the shaft is great. In the tunnel, we don't want to create a path for a sinkhole to develop, right? For settlement, piping of material, particularly in sands, through even a boring that has been backfilled, right, properly, can still create instability in the soil profile, and we don't want to drill right through our tunnel envelope. So a little bit offset would be good. Okay. Some acronyms: GIR, GDR, GBR. What is the difference? And this is something that has developed in the last really 20 years, probably more so in the last 10. Texas, I will say, has been a bit behind the curve of other parts of the country because we haven't had as many tunnel projects happening. That's changing. So what are the reports? So we'll start with GDR. So the GDR is a data report. So it contains factual information, not interpretive information. It's part of the contract. It should be part of the contract documents. It needs to be referred to in the specifications in the front end documents for that reason. If the GBR is not comprehensive and maybe not well written, it can be used to resolve disputes, but it shouldn't. The GBR should govern that first. So it's a data report. It's generally like 1,000 pages on a big tunnel project. You've got lots of borings, lots of lab testing, a lot of information. It's important to have in the record, but it's not our initial go-to, in part because it's so voluminous. All right, so what's a GIR? So GIR is a geotechnical interpretive report. We've seen these a lot. I see these a lot in Texas on underground projects. So it's an interpretive report, right? So it's taking the data from the data report, interpreting it. How is the ground going to behave? What should we expect to find? It provides some summary analyses of data sets. It's often intended to inform the design of the project. To say, okay, structural engineer, here's what you need to do for your shaft. Here's how much ground and earth pressure and water pressure you can have on the shaft walls. This is not intended to be used by the contractor for bidding, though. Not part of the contract. It is an interpretive report for design purposes. Sometimes I've seen these intended to replace a baseline report, but if they're not in the contract and they're not part of the contract bidding package, or even if they are part of the bidding package, but they're not part of the actual contract and enforcement of the contract, they don't serve the full purpose. So, useful tool, but not as important or useful as the GBR. So, GBR is the primary contractual interpretation of subsurface conditions. It sets baselines for what will be expected to be encountered. Doesn't mean it's going to solve all of our problems. It doesn't mean it encompasses all possible outcomes, but what should be expected to be encountered. It provides everybody a single contractual interpretation. That's really important. Everyone's focused on this document, which is concise. So we can read it in 2 or 3 hours, 30 pages, maybe 50 pages, not 1,000 pages like the GBR. And it gives everyone the same information bidding. When a contractor bids a job, it's a lot of effort to put together a bid. We want them to focus on what's most important. And that means concise. And a tunnel project may have a couple thousand pages of specifications. It's going to have 100 sheets, maybe on drawings. That's a lot of information to get through. I think the GBR is as concise as possible. So what are we doing in Texas? How have we been doing this? So not in all cases, but in many cases, we are still under the data report, interpretive report model. So the advantage of that is it doesn't cost as much from a design services perspective. In my opinion, that's the only advantage. Disadvantages are the GIR is generally too vague for use for a baseline. It has no use for bidding purposes. It presents, because of its vagueness, presents a lot of ambiguity, which can be problematic for litigation. Lawyers love ambiguity, as we are seeing in a political environment right now. Any ambiguity is an opportunity for a lawyer to get involved. So we want to avoid that in a baseline report. And the GIR, because it's an interpretive document for design, is just too vague generally. And it potentially results in inflated bids because of the perceived risks or things it doesn't talk about. So most of the United States, and I'm happy to say in Texas now, especially on larger projects, even on microfilm projects, we have GBR and GBR. So all the stakeholders, the owner, the engineer, weigh in during design through the baseline report. The risks are explicitly managed by the baseline set, and it provides a basis for bidding. So it has a higher upfront cost. And so the natural question is, how much does this cost? So you're already doing all the data collection, or you should be, for the data report. But what does a baseline report cost? Well, generally speaking, the baseline report doesn't cost that much. And we're talking $30,000 to $50,000 in that range. It's certainly less than $100,000. It is an interpretive report. I would argue it's not even a geotechnical report. It's really a risk management report that should be written not necessarily by a geotechnical engineer by himself, but with the project management team, with the other civil engineers, and with the owner, all engaged in that process. So the purpose, I'm being repetitive on purpose on some of these points, but manage the owner's risk through allocation, reduce ambiguity, communicate conditions, minimize disagreements, and provides a clear basis for adjudicating a differing site condition if it occurs. It's inbounds, out of bounds, right? And if we have that, the field of play set, something's out of the field of play, then it's pretty clear that we don't need to litigate this. It's like, okay, well, that's out of bounds. We'll pay for that. Or that's inbounds, we're not paying for that. It becomes a pretty clear way to adjudicate those things. So because of the collaborative nature, it is a good risk management tool. Just in the fact that you're putting it together makes you think a little bit harder about how the grounds behave. What should we allow for shaft excavation support methods? What should we allow for tunnel excavation support methods? What shouldn't we? Common basis for bids. And during implementation, it's a very useful tool. So these have been going on in the United States since the mid-1990s. There's a couple different iterations of the ASCE guidelines. So the gold book, the one that's shown that's in the bottom right-hand corner there, is the current best practice manual. It also, like the baseline report itself, is not long. It's a pretty small one. It's actually so small you sometimes lose it on your bookshelf. It's squished between two larger books. But this came to happen and be required because construction costs spiral out of control. When jobs don't go well and they cost a lot more money than they should, the owner is unlikely to do that kind of job again. And we've seen this on tunnel projects in some instances where they had products that were very expensive or had challenges during construction. The owner is now hesitant to do that kind of job again, even if they need the asset. So how can we prevent that? Well, GBRs were developed to help make jobs go better, reduce risk for all parties so that better outcomes happen. I don't need to belabor this point too much longer, but the GBR itself is actually kind of an excellent summary of the bidding of the project document. It's a summary of what can be expected. So not that you shouldn't read the specs or you shouldn't look at the plans, but the GBR, the methods it talks about and how it summarizes material is very useful to get a pretty quick look at what's intended for construction. And important, it takes precedence over the GBR. All right, so what is it not? We have to talk about what it is. What is it not? It is not simply a regurgitation of data from the data report. Sometimes I've reviewed GBRs that are just a bunch of data, a bunch of graphs and information, and no interpretation, and no behavior discussion, no use of the Tillman's classification of is this ground going to be flowing or fast raveling. That's not the point. It also is not a warranty that these conditions are going to be encountered exactly as portrayed. The earth is variable, right? And it's impossible to predict it precisely, but it is intended to provide you a range of information that you can have confidence that it should fall within that range. It's not a specification. So we want to talk about, in some cases, means and methods in the GBR, but it should not take the place of a specification, right? we get too much detail in the GBR, that needs to go in a specification. It also is a non-intent to push everything to the contractor, right? The GBR, by its purpose, should accept risk for the owner. And by doing so, they should reduce their cost at bid time. So, talked about this brief. The briefer the better. For a small, microtunnel project that doesn't have a lot of variable ground conditions, this thing might be 20 pages long. We aren't being paid by the page count here, right? So, briefer the better. The GBR should talk about those things, right? The owner needs to be involved. This isn't a, hey owner, here's your baseline report. Take it or leave it. It's a risk discussion that should be done in concert with the owner. It's part of that. Can the owner access change order funds without having to go to city council? Or how much money can they get without having to go to city council? Could we set the baseline a little more aggressively, encourage more aggressive bidding, but understand that if we do that, it might be a change order. But if we can pay for that change order without a whole lot of heartache, that might get us a better bid, and that risk may never occur, right? So might save money in the long run. Realistic baselines will result in lower overall cost. All right, so I've talked a lot about the baseline is the line in the sand, it's the field of play. Baselines describe the anticipated conditions. It should be realistic reflection of the available information. So one kind of cool thing about baseline reports is that they don't only have to just talk about what data you collected in the project. So they can say, we have these 5 or 6 borings for this project, and none of them hit a boulder, right? But we know that a mile from here, another project hit a bunch of boulders. We didn't encounter any boulders in our investigation, but we suggest, contractor, that you plan to encounter a couple boulders. Couple is actually not a very good term. We'll talk about that in a second. But say encounter 4 boulders. Those boulders are going to be less than 24 inches in the longest dimension, right? And they are going to have this compressive strength. They're going to be limestone, or they're going to be granite, or depending on where you are in the country. And that's the baseline. So if the contractor hits 3 boulders of that size, there's no change order, because that's the baseline. If they hit 6, well, they only baseline 4. And so then the question is, did the extra 2 boulders negatively impact the operations? Because to have a change order, to have a different site condition, you have to have 2 things. You have to have a different condition and a condition that caused a negative impact, right? It's not like, oh, well, the ground was different. It's like, okay, well, did it cause a problem? And the answer is no, then there's no change. The baseline sets what's in play, contractor's risk, and what's out of play, owner's risk. Now, we could set the baseline very wide and say, well, the rock quality of this, the RQD, is going to be anywhere between 10 and 100 on the scale. That's about the whole range. And maybe that's true. Maybe that variable condition exists. But if 3/4 of the RQD is between 70 and 90, should the range go all the way down to 10? Or should we expect that the actual range is higher? If you make the ranges go too wide, litigation has proven that those ranges will be thrown out in court. And the contractor will say that this baseline report is not reliable. And I had to go to the GBR and make my own assumptions. So we need to be reliable and make those realistic reflections. All right, so what are we baselining? What kinds of things we're baselining? So soil conditions, strength, right? Unit weight, is it abrasive? How permeable is it? Are there going to be boulders, right? Rock strength, all those kind of things are going to be baseline. Behaviors are going to be baseline. Firm, rattling, running, how the ground is going to behave in response to certain excavation methods. So maybe we allow different kinds of excavation methods, maybe we don't. So if we're saying it has to be pressurized space, I don't care how the ground is going to behave in open shield tunneling, because we said it's got to be pressurized space. So how is the ground going to respond to a pressurized space machine? Those are all things that can be baseline. So if you look at the baseline report manual, it lays out the report structure. So your baseline report should have these 9 sections, right? And these are, again, not tend to be voluminous, but discuss things. The previous construction experience section is really important. I mentioned that a couple slides ago about the boulders. Just because we don't hit anything in our investigation, if there's information nearby, this goes back to experience, right? Hire somebody, an engineer and a geotechnical engineer who's done work in the area, so they can say, okay, hey, this job didn't have this weird problem, but I know nearby there was a problem. Talk about it in GBR. It's important information to share with the contractor. But the contractor may not have local experience. Maybe a national contractor who have done work here and not realize that risk is there. characterize ground conditions. Grouping those ground conditions into units is really important. We'll talk about that in a little bit. And then how is it going to behave during construction? All right, so some examples. What does this look like? All right, so we did a project in Houston, put a baseline report together, and this is in soil, right? So in Houston, do a rock tunnel, you have to be really, 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 really deep, like thousands of feet deep. So everything in Houston soil. So we grouped all of the borings into 3 units. Unit 1 was clay, unit 2 was sand, and unit 3 was cemented sand. We said, okay, unit 1 is going to be, these are the properties. So you can see the in situ weight, 130 pounds per cubic foot, with a range of 120 to 140. So that baseline value is right in the middle of the range. Plasticity index is 30. The range was 13 to 42, but we're saying, hey, the mean of that, what's likely is going to be on the upper end of that range, or towards the upper end of that range. Friction angle is kind of right in the middle. Compressive strength, baseline value of 5,000. So the range is 2 to 6. So you could hit a 2,000 one, but most of this is going to be 5,000. So in this case, so if they encountered a soil that had a compressive strength of 8,000 pounds per square foot, that's outside the range. That would be a change order if it impacted their operations. But what this allows the contractor to do is say, okay, that clay, I need to specify my machine that can handle a high clogging risk clay with these properties and excavate it efficiently. He doesn't need to provide a machine that can actually do everything, right? He needs to focus his machine, cutter head design, type of machine to solve that problem. But also there's sand, right? So there's the sand values, and also there could be cemented sand. So in addition to just saying, here are the 3 values, 3 units, it's important to say, okay, how much of each unit should be expected? So the tunnel's 1,000 feet long. How many of those 1,000 feet, what percentage of that 1,000 feet is going to be clay? What percentage is going to be sand? What percentage is going to be cemented sand? Is there going to be conditions where we have mixed conditions, where it's sand in the bottom, clay on top, or vice versa? How thick is that cemented sand layer, right? That's something that's baseline here. That's 12 inches thick. Might be 6 inches to 2 feet. So if somebody hits a 3-foot thick layer of cemented sand, then, or it's stronger than 9,000 PSI, that's a change order. If it's not, that's something that contractor's been told to expect as part of design. And it is not a change order for construction. That's something that's going to be quickly resolved with some discussion. All right, so this is an example. We've done some work in Houston with our partner Parsons Engineering, and they got, this is an example from a job that they did in Austin. I thought it was excellent, and I wanted to share it. So they baselined the ground to say that the limestone in Austin was going to be between 250 and 3,500 PSI. The highest test value they did, 3,100 PSI. So they gave themselves a little bit of a buffer, 3,500 over 3,100. And the first reach for that was the case, and the second reach was going to be clay shale. So the contractor said, okay, I'm gonna put my T-beam together with ripper teeth, which is more effective for softer materials instead of disc cutters. Disc cutters cut rock, right? They're better for hard rock. So reach 1, they encounter 5,500 PSI limestone, way outside the baseline, right? Cost time, cost money, right? And then when they got back to reach 2, they had to go back from the disc cutters to ripper teeth again. So there's different site condition. They tested the rock, they verified it, documented, cost went up on the project. So was the baseline wrong? Was it a mistake? I mean, initial reaction to engineers is like, well, I obviously screwed something up because we counted something that was different. I would argue that this baseline was not wrong, right? Unless, and this wasn't the case for this project, there was data that said, hey, this limestone regionally could be 6,000 PSI. All data they had said it was up to 3,100. They said, okay, we're going to put a baseline of 3,500 PSI. And that set the bidding for the contract. They probably got a more aggressive bid from contractors because of that. It was softer. And they found something different. It was obviously outside the baseline. So they didn't have to litigate it. They said, okay, it's outside the baseline. Let's fix it and move forward. So this is a good example for a few reasons. Number one, GBRs are not always right? Ground conditions are not always consistent. But we shouldn't, for this job, they shouldn't have said, okay, our limestone is between 250 and 10,000 PSI. Unless data says it should be. In this case, data didn't say that. So they baselined it properly, had a condition that was different, and used the GBR to litigate that, or actually not litigate it, just discuss it and solve the problem without having to litigation. All right, so what are best practices here? Ambiguous words: could, may, might. If it might be encountered, contractor can assume that it won't be encountered, right? We can always look at things half full or half empty. Contractor's trying to win a job, right? He's going to make assumptions that help him get his bid down. And if it might be encountered, he can assume, well, it might not. Qualitative descriptors are bad: high, frequent, occasional, short, long. Those are not good. Right? We want to minimize or eliminate use of those as much as possible. Do not repeat yourself. This is a good advice for specifications as well. Reference the GBR, reference specifications. Don't repeat. Be succinct. Want this to be read, right? Be explicit. Put things in bold text. Underline things that are important. Make it stand out. And use quantitative terms or terms that are defined by the industry, like the Tunnelman's ground classifications, that we can measure in the field. So conclusions about GBRs. Underground construction is unique. Different contract strategies are warranted. The risk management is worth it, and the GBR approach works. Write reasonable baselines and enforce them, and benefit from the many lessons learned on projects. Well, there's a lot of lessons learned. There's a lot of war stories on projects that have gone well and haven't gone well. Some of them used GBRs, some of them didn't. Sometimes GBRs are not well written, and they could provide more detrimental effect than positive effect. All those things are important to vet out of the project. So with that, we have 10 minutes left for questions, and I'm happy to provide my insight on how we can use this tool, amongst others, for project risk management. And like I said, my email's on there, brian.gettinger@freeze.com. I'm pretty active on LinkedIn as well, so I look forward to connecting you on there. I often try to go through the attendee lists on these things and add people on LinkedIn so we can, connect in the industry on things. Happy to answer questions as long as they're not too hard. Do our best today. Start sharing and we can open that up.
If you have some questions for Brian, please type them into the Q&A. And let me ask you one question, Brian. What is the most difficult tunnel project you've ever worked on, and why?
Yeah, so I had the pleasure to be part of the construction management team for a project in Columbus, Ohio. And Ohio has limestone like we do in Texas, but it's karstic. So karstic limestone has had, over the years, the mineral deposits have eroded large voids in the rock. And those voids might be 2 inches, or they might be the size of a car. Don't know. And they're randomly distributed. And so that we did a tunnel there, and we had thousands of gallons per minute of water flowing into our tunnel that was not anticipated. One of the strange things that happened there, they did a very thorough investigation. They had a baseline, they had a document. Actually, it wasn't a baseline report; it was more of a GIR. But there were also some very high angled joints in the rock, and they were filled with clay. And sometimes when you do a boring, you don't hit high angle joints in rock because you might not be at the right angle. And also sometimes the clay and filling washes out. And so we thought those joints wouldn't make much water, and instead we had water features in the tunnel. And water is often one of the biggest challenges on a tunnel project because you're underground and there's nowhere to drain the water without pumping it out. So that was a challenging project. It was a 5-mile long, 20-foot diameter tunnel. Got built, got done, but not without a lot of hand wringing and heartache because of some of the conditions that were encountered on it. So there's lots of lessons learned. I kind of cursed myself, like, man, this job's really hard. I wish I had an easier job. But then you realize that the jobs like that are the ones you learn a lot from, because now you know how you might do it differently next time. Like maybe in that case, you drill a hole instead of vertical hole. There's high angle joints. Maybe drill a hole at 15 degrees perpendicular to those joints to see how it intercepts it differently. Good question. Thank you.
All right, we have a question from James. If relying on local experience regarding known analogists, where did the question go? Oh, it's gone. All right, here's another one. How does the project delivery method change the use of GBR, CMR, design build? Is this just a change of where the line is in the sand?
It is. So the GBR process is different for a design build project than it is for a design bid build project. So design bid build project, essentially what we walk through today, is included. The GBR is included as part of the bid set the contractor will bid on. For design build project, generally that design is taken to like the 30% design level, and then it goes out to a design build team. So in many cases, in most cases, a GBR for bidding will be produced for the 30% design set. Then the design build team will actually itself produce a baseline report as they finalize their construction costs during the design build process. There is a bit of you're creating the process in the in-house. In that case, the contractor is involved in the development, but it's important. It's actually quite useful. The contractor can help set that baseline and say, okay, if we get something outside of this, it's a change order, or this is what we accept as our risk. So the process is a bit different for design build versus design bid build.
Another question, how should we identify the method of application? That is, depending on various factors, which method out of the GIR, GBR, and GDR should be applied?
So I will err on the side of you should use the GBR unless. So we should use GBR first, unless the conditions are very well known and the product is very small, and the perceived risk of complications due to the conditions that are unexpected is insignificant. So if we're talking about a county road crossing in a non two-lane road that doesn't have a lot of traffic, that we know other jobs been done nearby, it's all clay or it's all rock, and it's 100 feet long, maybe the GBR isn't necessary for that. But if microtunnel is crossing waterways and it's a few hundred feet long, 1,000 feet long, even a small diameter microtunnel, in my opinion, should have a GBR, or one should be considered or discussed as part of the scoping effort. And also, large tunnel projects, anything using a tunnel bore machine should absolutely have a GBR, in my opinion.
The question, going from A to B, how do you navigate or stay on course? And I can remember getting in a project that we were involved in Taipei, Taiwan, where the subway was being drilled with a tunnel boring machine, and it got offline. And the effort that had to be and the redesign that it had to go into play. So a good question, how do you navigate or stay on course?
Well, you need a good tunnel surveyor. Tunnel survey is a lot different than ground surveying, because everything's tied back to a point in the shaft. So if anyone bumps into that control point in the shaft, or gets hit by a piece of equipment, you can have potentially have a problem. The equipment now is capable of putting things within an inch or less than an inch accuracy. But you have to have the survey set up the right way to do that. So there's even microtunnels. We can do curved microtunneling drives with gyroscopes and things. But it is just like risk management is different. Surveying underground is different. The technology can keep you online and grade, but only if it's being operated by folks who know what they're doing. So good tunnel surveyor is an important part of that, because we don't want the tunnel to be 4 feet above or 4 feet to the right or where it's supposed to be, because it has to tie into something else somewhere.
Yeah,
that, like you said, is a very expensive thing to realize at the end. Usually also because when a tunnel bore machine breaks through, there's a big celebration, right? The mayor wants to come, everyone wants to go down the tunnel, and if it misses, it's a little bit embarrassing. Not the right spot, so it's good to avoid that.
All right, any input on how you approach projects in different cities throughout Texas? Are some areas more difficult than others? And how do you adjust different contractor preferences?
Yeah, so every city, there's lots of cities in Texas. We'll say there's 4 big ones: San Antonio, Austin. We'll say Dallas and Fort Worth together. Nobody crucify me. I'm in Houston, right? So North Texas is all one mass. And then Houston. So Houston's all clay, right? San Antonio has got clay shales and some other soils. Austin has got some really good limestone in some places. In all cases, we're crossing creeks and stuff. We get a little kind of mixed conditions. Dallas has got some really favorable limestones and shales. So how you handle that is that you need to have geotechnical engineers that are experienced working in those areas, right? That have done other projects that can rely on their lessons learned. Say, okay, yeah, we did a project, even if an open cut or deep excavation project in the Eagle Ford Shale, right? And this is how it behaved. Or we did a project in the Austin Chalk, and this is how it behaved. Or the Navarro Clay in San Antonio, this is how it behaved. Or in Houston, we hit the sugar sand and it behaved like this. Because every area is different, and that applies outside of Texas as well. So experience in that kind of ground condition is really good. Also, historical data research is really valuable. I mentioned the Waxahachie Super Collider project that didn't ever come to pass, but hundreds of borings were drilled. Lab testing was done on all kinds of projects. So the shales that that project was intended to be excavated in are very homogeneous across the large region, all the way up into North Dallas. And so there's data we can take from that and apply it elsewhere.
All right, and then what is the shortest tunnel that should be considered for an EPBM equipment to be used?
Sure, great question. So an EPBM classifies as a pressurized space machine. So the follow-up question is, what's the diameter, right? If it's if we need to do, and we don't have to, it's just a hypothetical question. So if this 100-foot long, say it's a 100-foot long crossing, right, and it's 8-foot diameter, then that's a microtunnel project. We're probably not using EPBM. We'll probably use a slurry pressurized space microtunneling machine. But if that 100-foot length is 25-foot diameter, it'd be kind of an odd project. But if it needs a really wide opening, not very long, then an EPBM machine is 300 feet long itself. Not a great application for a 100-foot long tunnel. So there's sort of a, you need to know the length, right? Sort of the ground conditions, and then the diameter, and that's going to inform what the right method of construction is.
If relying on local experience regarding the known special conditions which were not encountered in the exploration, can ambiguous words such as may or could still be used in the GBR?
Yeah, great question. So this goes back to my boulder example. It's like we didn't hit any boulders, or we didn't hit cemented sands, for example, in our borings, but we know this is a problem because this other tunnel project hit it, or we had excavation that hit it. How do we include that in the document? So the cemented sands question is one that we brought up on this Houston project, and that we didn't have those in the boring logs. We didn't hit them. And so there's a lot of interpretation required for the geotechnical engineer and the owner to understand, okay, what should we assume? What's the worst case we want to price in? Now, if we had not said at all cemented sands, the tunneling contractor might have a different cutter head design. It probably will cost a little bit less. But if that cutter head design for clay and sand hits the cemented sand at 8,000 PSI, it's going to go nowhere, right? So we made a choice and said, okay, we want to ensure that the cutter head design can handle it. We know it's going to increase the bid price a little bit because you have a more robust cutter head design that has some cutting tools that could cut through that 8,000 PSI cemented sand. So we went ahead and baselined it. If we would have just said might encounter cemented sands in the GBR, then the contractor would say, okay, well, he might not. And then that document on that issue is essentially silent. Well, the contractor would say, well, you said might, I thought might not, you thought it might, and then it's an argument that may get litigated. Whereas we chose, okay, 6 foot to 2 foot thick cemented sand is possible based on regional behaviors. Even though we didn't hit it, that gave us, covered that risk. It did increase the initial cost of the project. That's the discussion we have with the owners. Are they willing to take that risk and put it in the bid price? Or do they want to hold it out and just hope they don't hit it? It certainly costs less to include it in the bid, but it's money you may not have to spend at all if you don't put it in the bid, but it'll cost maybe 10 times more if you don't. So like I said, this should be a discussion with the owner about the risk tolerance for the project.
Well, Brian, thank you so much for answering the questions that we got to today. And as Mike noted in the chat room, there were a number of questions that we haven't been able to ask because we're just about essentially out of time. But Mike did indicate that he will email you, Brian, all of the remaining questions and ask you to respond to them. And then he will send out the questions and answers to all of